All right, folks, we're going to take a look at the law of conservation of momentum in this video lesson, and it will act as a continuation on the previous lesson of just base momentum and impulse. And now we're going to look at how momentum is conserved through our collisions. So the first big idea that we really look at here is that in an entire system, in a closed, isolated system, total momentum is not going to change. That is really similar to the idea of the law of conservation of energy, where in a closed, isolated system, the total amount of energy is going to stay consistent, right? That's not going to change either. The difference, what we see between momentum and energy, though, energy, we are allowed to have the type of energy change, right? We could go from kinetic to gravitational potential, or elastic potential to kinetic, or kinetic to sound. And in collisions, we could lose kinetic energy, and that would transfer to other types. Well, here in momentum, our momentum before is going to match our momentum after, and we are not going to see momentum take on other forms, right? We're going to have the motion of an object. It's going to have momentum. Whatever that momentum is at the beginning of a collision is going to be the same after the collision in total. Now, some objects can then gain momentum while others will lose momentum. Just like we looked at before, momentum is a vector quantity, so you really have to be careful on your directions here. It is important if two objects are moving to the left, or one object is moving north and something's moving south. That becomes a pretty critical piece of the puzzle here. Now, what we see in the animations, these are called Newton's cradles. And the figure in the top right, you're going to see, hey, we got one of those spheres is moving up, you release it. It's going to have momentum at contact with the rest of the spheres. That momentum is going to transfer to each one of those spheres until it gets to the last one, which will then swing out. That will then continue in the pendulum motion that we see in the bottom right. Now, one other ways that we can look at this here with the actual Newton's cradle itself, right? So by taking a look at this one here on my desk, we can do a couple of different experiments and a couple of different demonstrations to show how momentum is conserved. So if we do the basic, pull back one, we're going to see one kicks out each time, right? One and one is going to be kicked out. If I stop this, just to show that conservation again, if I pull two of the spheres and let it go, now we see two spheres going back and forth, right? Because the total mass that was there, it's going to have its velocity. We're going to see that total momentum conserved there. This trend continues if I do three spheres. So if we go three and drop it, we're going to see three of them move, right? Where now the middle one is going to move the entire time. We can go even more dramatic and we can do four. And if we do four, right, we get four spheres are constantly going to be in motion. And other cool ones that we can do, if we do one and one on each side, momentum is going to be conserved, and those are going to be the only ones that will move. Right? So we're going to see them fall inward. That momentum is going to transfer, and it's going to pass through, and it's going to kick back out the other side. We can do two and two, and we can just leave the center one stationary, and we're going to get the same result. Both of them are going to go inward. That momentum is going to transfer, and we're going to see it just swing back and forth. We can go two and one. And if we go two and one, we're going to watch it rotate. We're on either side, two kick out, and then one kicks out. And we can go three and two, where if we release it, now we're going to see patterns of three and two spheres together. Where each one of these is demonstrating our conservation of momentum through collisions, right? What we have before has to be there after, right? That's what we see. So with this law of conservation of momentum, whenever two objects collide, the momentum before has to match the momentum after. And this could be for two objects, three objects, four objects, however many objects are in our system, the momentum pre-collision has to match the momentum post-collision. So here on the left-hand side, we see the initial momentum of objects 1 and 2, and on the right side, we see the final momentum of objects 1 and 2 respectively. We can also break that down as it shows to be m1v1i plus m2v2i for the initial equals m1v1f plus m2v2f on the right-hand side for the final. Because we can then break down momentum into its individual components. Now, other variations that we can look at here for our conservation of momentum, as we get different types of collisions, well, what if they stick together in a perfectly inelastic collision? Well, if we take a perfectly inelastic, so again, that is going to be they stick together. In that type of collision, they're going to start separate, so M1V1I plus M2V2I. But because they stick together, now we can treat them as one mass post-collision. So M1 plus M2, and they will be moving at the same velocity because they're moving off as one object. So M1 plus M2, we can take the sum of those because they're combined, times that common velocity. Now, if we look at what would be deemed as an explosive collision, and an explosive collision is going to be when two objects start together and then somehow separate, right? Whether they break apart, they fracture, whether it's they just push apart. So what this ends up being is we have one object, which is going to be the sum of our masses that are present, and then they are going to somehow separate. And when they separate, each one of them is going to have their own unique final velocity, potentially, right? That they don't have to be different, but they certainly can be. So our fundamental difference between these two, if you notice, our initial conditions for perfectly inelastic of two separate objects is how our explosive collision ends. And our perfectly inelastic, they end as one object, and for our explosive, they start as one object. So really we have three different ways that we can look at this. We have the traditional, which was on the slide. We then have perfectly inelastic and our explosive, each of them representing different types of collisions that could occur in different situations that we could see. Now, one thing that's unique about conservation of momentum, which we can do, but we could not through conservation of energy, we're actually allowed to find masses and velocities because momentum through a collision is going to be entirely conserved. We're not going to branch off into different types of momentum here. Whereas for energy, we could lose one type to gain another. Because we had different energies going on, we couldn't pin down the mass and velocity through a collision looking at conservation of energy. However, in conservation of momentum, we can, right? We can certainly find masses and velocities because momentum is conserved through collisions. So if we do a quick concept check here, we've got a Honda Civic and a Chevy Suburban, with the Civic obviously being much smaller than the Suburban is. The Civic is moving 50 miles per hour east, and it collides with a Suburban that is moving 50 miles per hour west. What direction will the Suburban be moving post-collision, and will it be moving faster or slower than it was pre-collision? So if we think about this problem, the Civic is less massive than the Suburban, but they're moving at the same speed, which means the Suburban is going to have more momentum. It has more mass, same speed, so we're going to have a higher amount of momentum. Now their directions are equal and are not equal, their directions are opposite. So because of that, in this head-on collision, the Suburban moving west has more momentum, so it will continue moving west after the collision. If you picture this, you have the Civic and the Suburban. And when the Suburban makes contact here, we're going to hit head-on, and the Suburban will actually push the Civic back towards the west. So each of these objects are going to be moving west after the collision, and they are each going to be moving much slower than the 50 miles per hour. Right? So because of this, after the collision, the Suburban is still going to have some of that original momentum because it had more to start with, even though the velocities are equal and opposite. Now that being said, we don't know any masses, so we couldn't actually figure out velocities of either of these objects post-collision without knowing their masses. And vice versa, if we knew their masses, we could find velocities post-collision. Now, if we check our math here a little bit, we have a 5 kilogram ball on the left, and that's moving at 10 meters per second when it hits a stationary 8 kilogram ball. After the collision, the 5 kilogram ball then moves backwards at 2 meters per second. So we want to know what is the velocity of the 8 kilogram ball. Here's what this looks like. 5 kilogram ball moves, we make contact. Initial velocity of 10 and 0 respectively. Post-collision, the 5 kilogram is moving at now -2 meters per second because it bounced backwards. The 8 kilogram ball is moving at some speed. Please go ahead and find this speed. Pause the video and then come back and make sure that you have the correct response. Okay, welcome back. Here's how we would go about this problem. Because these objects don't stick together, right? We have an inelastic collision here. We're going to have our initial velocity of object 1 is 10 meters per second, so we're 5 times 10 at the beginning. And object 2, the 8 kilogram ball, is at rest, so there's no momentum for that one. Post-collision, the 5 kilogram ball is moving backwards, so -2 meters per second, and we want to find the velocity of the 8 kilogram ball. So the initial momentum of mass 2 drops out, so the overall momentum in the system pre-collision is 50 kilogram meters per second. Object 1 of 5 kilograms has a momentum of -10 kilogram meters per second post-collision, so we can add that over and then divide the 8. So a little bit of algebra is going to yield us 7.5 meters per second in the positive or forward direction for object 2. Now, a quick additional practice that we can also look at. So we have a 35 kilogram kid who's going to run and jump on the back of a stationary toboggan with his friend on it to get it started. The toboggan then moves at 2.5 meters per second. And the friends in the toboggan have a combined mass of 90 kilograms. How fast was the kid initially running? So this is going to be our example of a perfectly inelastic collision where they're going to stick together. So we have our original look at conservation of momentum, right, which is going to be and this formula still works. I want to make sure that's clear, right? This is still a functional formula, but because they stick together, remember, we can go ahead and consider their masses combined at the end. So we have the 35 kilogram kid, and the entire mass of the toboggan with both friends is 90 kilograms at the end, which means the mass of the first kid and the toboggan by themselves before they were moving is going to be 55 kilograms. Post-collision, they will be moving all together at 2.5 meters per second. So the way that we can approach this problem is we have our 35 kilogram kid moving at some speed. We have 55 kilograms of mass that's not moving, so that momentum is 0. We have 90 total kilograms at the end, moving at 2.5 meters per second. And we know that the 35 kilogram kid will be moving in the same direction that the toboggan is, because he's going to run, jump on it, and it's going to get him to move in the same direction. So 90 times 2.5 gets us 225. We divide the 35 kilograms over, and we find a velocity of 6.4 meters per second for that first kid. So remember, with our conservation of momentum here, you are allowed to solve for masses, you're allowed to solve for velocities. We can also look at how we can manipulate our conservation of momentum to fit specific scenarios where objects either start as one mass and separate, or objects start separate and then combine to form one solid mass post-collision. So we can look at conservation of momentum, understanding that it's going to be the same before and after the collision, and we can use that to find measurable quantities about the objects themselves within the motion and within the collision. Thanks, guys.